This circuit simulation verifies the calculation of secondary voltage from the value of primary voltage and the turns ratio. The circuit has been constructed using the given values of transformer primary and secondary winding turns and the applied primary voltage. The turns ratio is equal to N sub P divided by N sub S. The problem is solved using the equations on the screen. E secondary is equal to E primary times the number of turns in the secondary divided by the number of turns in the primary. The simulation is turned on to confirm the calculation. Since the secondary voltage is greater than the primary voltage, this is called a step-up transformer. This circuit simulation verifies the calculation of secondary voltage from the value of primary voltage and the turns ratio. The circuit has been constructed using the given values of transformer primary and secondary winding turns and the applied primary voltage. The turns ratio is equal to N sub P divided by N sub S. The problem is solved using the equations on the screen. E secondary is equal to E primary times the number of turns in the secondary divided by the number of turns in the primary. The simulation is turned on to confirm the calculations. Since the secondary voltage is less than the primary voltage, this is called a step-down transformer. This circuit simulates the calculation of transformer primary current and secondary voltage. The circuit has been constructed using the given values of the primary voltage, the transformer turns ratio, and secondary current. This problem is solved using the following equations shown. I primary is equal to the number of turns in the secondary divided by the number of turns in the primary times the secondary current. And E secondary is equal to E primary times the number of turns in the secondary divided by the number of turns in the primary. The simulation is turned on to confirm these calculations. This circuit simulates the volt-amp power rating of a transformer. The power handling capacity of a transformer is always rated in apparent power, or volt-amps. This scenario demonstrates that for an ideal transformer, the input volt-amps is always equal in value to the output volt-amps, or E sub P times I sub P equals E sub S times I sub S. This is seen by turning on the simulation and comparing the product of the primary voltage and current and the product of the secondary voltage and current. In this case, both are equal to 100 volt-amps. This circuit simulates the calculation for solving for the secondary current, primary and secondary volt-amps, and primary current of a transformer. The circuit has been constructed using the given values of the transformer primary and secondary voltages and secondary load resistance. The problem is solved using the following equations. I sub secondary is equal to E sub secondary divided by R sub L. Then, volt-amps of the secondary is equal to E sub secondary times I sub secondary. Since the volt-amps of the primary is equal to volt-amps of the secondary, I sub P is equal to the volt-amps divided by E sub P. The simulation is turned on to confirm these calculations. This circuit simulates the calculations of the secondary voltage of a transformer when the primary side is operated at a lower voltage level. The circuit has been initially constructed using the rated primary voltage applied and then dropped to a lower voltage. The problem is solved using the equation, the new E sub secondary is equal to the new E sub primary times the ratio of the original E sub secondary divided by the original E sub primary. The simulation is turned on to show the original values, and then the source voltage is changed to confirm this calculation. This circuit simulates the calculation of the primary current of a transformer when the primary voltage and secondary voltage and current are known. The circuit has been initially constructed with meters connected to display all known values. The problem is solved using the following equation: I sub primary equal I sub secondary times E sub secondary divided by E sub primary. The simulation confirms the calculations. This circuit simulates how to verify transformer polarity labeling. The location of the H and X terminals indicate whether the transformer was designed to be either additive or subtractive. A transformer is said to have additive polarity when terminal H1 is diagonally opposite terminal X1. A transformer is said to have subtractive polarity when the terminal H1 is adjacent to terminal X1. This polarity test circuit verifies that the transformer markings indicate a subtractive polarity. First, the simulation is turned on with normal connections. The transformer has then been reconnected for subtractive polarity. This circuit simulates transformer voltage and turns ratio calculations for a three-phase Y-to-Y connection. The circuit has been constructed using the given values of primary and secondary phase voltages. The problem is solved using the following equations. E phase primary is equal to 4800 volts. E line primary is equal to E phase times 1.732. E phase of the secondary is equal to 480 volts. E line of the secondary is equal to E phase times 1.732. The turns ratio is equal to E phase of the primary divided by E phase of the secondary. The simulation is turned on to confirm these calculations. This circuit simulates the different types of AC voltages available from a delta to Y transformer connection. Note, the 4-wire secondary provides a neutral point for supplying line-to-neutral power to single-phase loads. Three-phase loads are supplied at 208 volts, while the voltage for single-phase loads is either 208 volts or 120 volts. The loads connected to a transformer should be connected so that the transformer is electrically balanced. Perfect electrical balance occurs when loads on a transformer are connected so that each phase of the transformer carries the same amount of current. Although perfect balance is rarely, if ever, achieved, it is something that you should strive for. The simulation is turned on to examine these characteristics. This circuit simulates transformer current calculations for a three-phase delta to Y connection. The circuit has been constructed using the given values from the transformer nameplate data. The problem is solved using the equations on the screen and the equations secondary I of phase is equal to the secondary I line. The simulation is turned on to confirm these calculations.